we're still not like really manipulating the formulas and stuff. So we're looking at properties of limits that are always true. And so we're going to say if we know this limit and we know this limit, we can do different things with them. So you'll see what we're talking about. We're not going to get into like really dealing with like 2x squared plus 7x plus 5 and having to figure out what limits are from that until tomorrow. So capital L, M, C, and K are all real numbers in this. So I just took a screenshot of what comes from the book with this. So your limit laws here, you have a sum rule. That just tells you if you know the limit as x approaches c of f of x is L, and you know the limit as x approaches c of g of x is M. What it's telling you here is you can just take the limit of those two expressions separately and add them together, right? So if you are doing the limit of two functions added together, it's just the limit of each function there. The same is true for subtraction. If you have the limit as x approaches c of f of x minus g of x, L minus M, right? A constant multiple rule right here, sometimes that'll be called a scalar multiple. When you have a number right here, so that k might be a 3, it might be a 2, it might be a negative 4. It can sort of be pulled out front right here like this, where you're just doing k times that limit, which is L, is what they told us there. So you can just multiply the answer you would already get by that. If you're doing the limit of f of x times g of x, your answer is going to be L times N, the limit of the first one times the limit of the second one. Same thing is true for division, except for they do give us this exception right here. M cannot equal 0. Why is that? Can't divide by 0, that would be undefined, right? So they have to put that condition right there. So unless you're getting a 0 for that limit for your g of x, you can just divide right here. And if you've got an exponent, really they could have put power rule and root rule together, because if you guys remember, when you have a root, like the square root of the n root of L, it is like L to the 1 over n, so it's really the same as doing an exponent here, but if you're raising something to a power or taking a root of it, you can just take the root of whatever that limit was. So let's just look at some examples of stuff that you will see here. I'm going to go overboard on the first couple that I do, so you understand how like these properties are applying, but I think you'll see once we get a little further, like it's pretty easy to complete. So without showing the work I'm going to show on these first couple. So they are giving us the information that the limit as x approaches 2 of f of x equals 5. The limit as x approaches 2 of g of x is 6. Limit as x approaches 4 of f of x is negative 1. Limit as x approaches 4 of g of x is 9. So we don't know what these functions are, and we only know these limits at these points here. So if I have something like the limit as x approaches 2 of 2 f of x over g of x, then I can sort of break this down. So the quotient rule tells me that if I have two things I'm dividing, I can take the limit of the top and the bottom separately. So what this would look like, and I'm going overkill, I would not normally show this amount of work. It would look like this. I'd have the limit as x approaches 2 of 2 f of x divided by the limit as x approaches 2 of g of x. And then I also have the constant multiple rule that tells me if I'm taking a 2 and multiplying it by that f of x, I could sort of pull that out front right here, and I could write it this way: 2 limit x approaches 2 of f of x over the limit as x approaches 2 of g of x. Now, normally when I'm doing these problems, I do this part in my head. I don't really write that out. But I am told that the limit as x approaches 2 of f of x equals 5. So right here is the limit as x approaches 2 of f of x. I can replace all of that with 5. Right? In a similar manner, in the denominator, the limit as x approaches 2 of g of x is given to me up here. Limit as x approaches 2 of g of x is equal to 6. So in the denominator here, I'm going to be dividing by 6. Right? So I got 10 divided by 6, which is 5/3. And that is my answer. So normally, I would not go to these links for this, right? Because what you can kind of do is like picture in your mind what is happening here. Well, I got the limit as x approaches 2 of g of x. Well, that limit as x approaches 2 of g of x, that's just 6, right? And it would be, hold on just a second. It would be better here if I had put a bracket around this because it's supposed to be the limit of the whole thing. That is my mistake on that typo. So we're doing the whole thing. So like whenever I do this, I'm gonna write it out the proper way, and then I'm gonna just show you what I'd actually write. So like I'm gonna have the limit as x approaches 2 of g of x, and then I would also be doing the limit of this other stuff. That 3 is a coefficient. It can just be sort of pulled out. Limit as x approaches 2 of f of x right here. So this is just going to be 6, and over here this is just 5. So I got 3 times 5, and so 6 plus 15 is going to give me 21. So whenever you do this here, for the next one, we got limit as x approaches 4 of f of x minus 2 squared. Essentially what you can kind of do, well, you're taking the limit of everything here, right? But the only thing that really like changes is whatever that f of x is, right? The limit as x approaches 4 of f of x. Let me use a different color because that's not really red right there. Right? The limit as x approaches 4 of f of x is negative 1. So that f of x, when we take its limit, it is going to become negative 1. When you take a limit of a constant, which is just 2, it just stays itself. It's just 2. And then the power rule tells us that we can just leave that alone. Right? So rather than writing it all out properly with limit notation, I typically shortcut this here, and you're going to get negative 3 squared, which will give you 9. And so for this last one over here, let's see, what color have I not used? It's orange. So for this last one over here, the limit as x approaches 4 of g of x is going to be 9. So we're going to end up with, we're going to put right there, when we do the limit of this stuff, we're going to get 9, right? And the root rule and the coefficient rule tell us that the other stuff basically just stays the same. So I'm going to get square root of 9 plus 4 which is going to give us 3 plus 4, which is just 7 for that. Okay, all right, here. Okay. All right. Another thing that we'll look at are composition of functions. Composition of functions is when you're putting like a function inside of another function. F of g of x or something like that. So if you know the limit as x approaches c of g of x is L, and the limit as x approaches L of f of x is f of L, then the limit as x approaches c of f of g of x, you do the limit of the inside first, and you will get f of L for that, because this right here is going to be L. So, I think it's easier to look at an example for this. So if we're looking at these from equations, first of all, I'm sort of skipping ahead just a little bit by giving you this type of problem, but it is also like in the textbook, so I'd like to go ahead and introduce it. Technically, you're not really supposed to know how to do a limit of an equation until we get to the next section. But for us to use the book for our homework, we kind of need to know how to do this. So like what I would need to be doing first right here is I would need to be doing the limit as x approaches 3 of the inside function, right? So in this case, that would be the limit as x approaches 3 of 1 over x plus 2. That's step 1, right? That's the first thing that we're going to do. Now, I haven't shown you how to do this yet with an equation. We could graph it, maybe figure it out, but it is very, very simple for the type of problems that they're going to give you today on how to do this. If you can plug in the number 3 and it gives you a number, that's what you're going to do. You're going to plug in that number and that's what you get. So we're going to have 1 over 3 plus 2. We'll call this direct substitution as we look at this tomorrow. If you can plug the number in and it gives you a real number, it doesn't give you 0 over 0 or 7 over 0, like something that's undefined. If you get a defined number, that's the answer. So it makes it pretty simple to do this. 1/3 plus 2 is the same as 1/3 plus 6/3, or yes, 6/3, which is going to give you 7/3. Now that's just step 1, because that's just the that is just the value of the limit as x approaches 3 of g. Yes, and that is what we're going to do next, because what's happening here in step 2 that I don't really have room for, I'm going to adjust mine. I realize yours is already printed. Let's move this down a little bit. In step 2, what happens now is we are now doing like the limit as x approaches 7/3 of f of x. So that'd be our 2x minus 1. And so whatever you get right here for your limit for the inside function becomes what you're approaching in the next limit of the outside function. And everything you're going to see right now should be direct substitution. Yeah. Yeah. For right now, yes. When we start to learn how to do more complicated limits, we'll see some cases where you can't just plug the number in because you get undefined or indeterminate answers. But we'll look at that tomorrow. So today, everything that you get should be a direct substitution problem where you're just going to do 2 times 7/3 minus 1. And I do want you doing this like no calculator, because something like this is going to be on the calculator inactive section of the test probably. So we'll put this over 1. We'll get 14/3 minus 1. We're at 14 thirds minus 3 over 3, and we should get 11 thirds as our answer for that.
Can we put like the limit statement, would that still equal 11 over 3, or is that just the answer we get?
This is your 11 over 3 is your final answer. Yeah, it's your final answer. So like 7 thirds is not your final answer. It's an intermediate step where you're taking the limit of that inside stuff there. So like whenever we do one like 6, the first step would be to do the limit of the inside, right? So that would mean we're plugging in 0 to f of x, right? Our limit, so our first step would be the limit as x approaches 0 of 2x minus 1. And when you do a limit like that, you're just plugging in the number, right? When you plug in the number, you don't have to put limit notation anymore. 2 times 0 minus 1, and you get negative 1. And then the second step is that becomes the limit as x approaches negative 1 of the outside function, which is your g of x. In this case, that's 1 over x plus 2. So you're just plugging in negative 1 there. So 1 over negative 1 plus 2. That's just going to be negative 1 plus 2, which is going to give you 1. That is your final answer for that. Okay. Try f of g of x there for the last one. Freeze my screen while I do that one. You guys got an answer? What are y'all getting? Or are y'all having a problem? Should be a problem, right? So what's going to happen here? What is going to happen here is when you start trying to do that first limit, you get 1 over 0 plus 2. That is undefined. So whenever that happens, whenever you're doing a problem like this, we're going to see some crazy stuff happen on some graphs here in a minute. But on a problem like this, it's a direct substitution problem. If that is undefined, that tells us we've ran into an issue. We're going to say the limit does not exist for that. So if you're doing direct substitution like we're doing here, and you get a number over 0 as part of what you're doing, that's undefined. We're going to say that limit does not exist. If I do not think it will happen today, because I don't think they put this on here yet, if you get 0 over 0, that's a different scenario, and there could be a limit that exists, and that's what we're really going to study tomorrow. So, so just know that's an option, but I don't think you're going to run into it today. Okay. Now, to me, I think the first couple types of problems we've done here are pretty quick and pretty easy to do. The graphs are not long. The graphs can be confusing. So let's look at a graph here, particularly a couple types that we're talking about. Let me zoom out just a little bit so we can see the whole thing. So we've got F and H graphed here. And we are supposed to find the limit as x approaches 0 of f of h of x. So if we think about what we'll do here, we're doing the same thing that we did on the problems where we were plugging in those numbers, but we got to get our answers from the graph. So limit as x approaches 0 of h of x is the first thing that you're going to do. That's your first step. Do that limit of the inside. So what is my limit as x approaches 0 of h of x? Negative 1. Okay? Because both from the left side and the right side, I go to that negative 1. It's not defined at that point, but that's okay because you don't have to have a defined point at a limit. That is okay. So then my second step would be I'm going to be doing the limit as x approaches negative 1 of f of x. Ooh. What is it? What do we get when we look at the limit as x approaches negative 1 of f of x? There's vertical asymptote here. What it feels like we're getting that the limit does not, technically we are going to get the limit does not exist, but is it going to be like positive infinity or negative infinity? The way I have it written right now, I've got a double-sided limit. I'll be honest with you, I had probably taught calculus for 3 years before I did these problems right. Because I would have just said the limit does not exist. You got like these divergent here. And I'd probably taught for 3 years before I even really knew how to do these problems. Mm-hmm.
For the number 2, how do you get for the x's to the negative 1 instead of 0?
So whatever you get right here, like whatever you get for the answer to the first one, becomes what you're approaching for the second one, right? So that's sort of how you like do the composition of functions. So like whenever we're adding two things together, we just keep that x approaches 0, x approaches 0. But when we do this, we got to do the limit of the first one, and then that becomes what you're approaching for the second one when you do the outside. Now, this has an answer. And the answer is positive infinity. Okay? So let's talk about why. So if you look at the graph, positive infinity must mean we were only looking at the right side of the graph, right? So as x approaches negative 1 from the right, I get positive infinity. But you got to ask yourself, like, why in the world is it from the right? Because nothing here tells you that it's from the right. It comes from the graph of h of x. So as we're doing the limit, as x approaches 0, think about our y values for what's happening here, okay? So like up here, my y value is 4, right? And then here, I got 3. Here, I got 2. So as these points get closer and closer and closer to having an x-coordinate of 0, the y values are approaching negative 1. They are, the y values, so right here, y values approach negative 1 from above. Right? So it's like 4, 3, 2, 1, 0, negative 0.5, negative 0.9, negative 0.99, right? So those y values are approaching from above. If you look at from the right side of the graph, same thing. Y values, 3, 2, 1, 0. You're approaching from above on both sides. Think about what happens. The y values of the first one become the x values of the second limit that you do. So because both of your pieces of your graph from both the left and the right are approaching from above, this is a limit only from the right side, because the numbers are only like approaching from 4, 3, 2, 1, the numbers that would be on the right side there. So if both lines come from above, it is a limit from the right, and you only look at the limit from the right here. So this does have the answer of positive infinity for this one.
What if it's like one from the above, one from below?
Okay, if it's one above, one below, then you have to do a double-sided limit. So if this function had not looked like this, maybe if this side over here had done, something like that, right? And one side was coming from below, one side was coming from above, then we would say that the limit does not exist for this, because you've got a positive infinity on one side and a negative infinity on the other. So if it sort of crosses, from above and below, then it's going to be the limit. Well, you have to do the double side limit. The answer does not exist for that. It depends on what the graph of your other function looks like. If they both come from below, what would you do? You're going to approach from the left instead of approaching from the right. So you have to pay attention to that piece. And I didn't even know to do it at first. I think I had maybe the first or second year, I probably had never even seen one of these problems before. And I ran into it, and I was answering everything, and I was checking. I was like, I am wrong on this. And it took me a while to figure out what I was doing incorrectly there. Let's look at a couple more like this. So if I'm doing limit as x approaches 0 of f of h of x, first step would be to do the limit as x approaches 0 of h of x. So start with the inside. H of x is over here. What is my limit as x approaches 0? That is 0. Okay? Because as I go closer and closer to here, closer and closer to here, I'm going to that open circle right there. The y-coordinate is 0. H of 0 is 5, but that's not what we're doing for this. We're looking at limits, right? Now, it doesn't matter so much on this problem because you don't have undefined limits over here, or limits that don't exist over on this graph. But whenever I do my second limit for x approaches, it's going to be x approaches 0, but it's not this 0. It's that 0 right there. Goes right here. Am I approaching from above, from below, or from both sides? Whenever I look at this limit here. Both of these are from above. So that means that this limit right here is going to be a limit from the right. Now, it ends up not really mattering very much for this problem because when I look at f of x here, my limit as x approaches from the right is 1. From the left, it's also 1. So you could, a lot of these, probably one of the reasons I didn't realize I was doing these wrong is a lot of these problems, it doesn't really matter. It's just like certain ones that are going to be tricky, like the one that we just looked at. But technically, this is a limit from the right only.
Wait, it's not negative 1.
Oh, yes, it is negative 1. Thank you. And that will be your answer for that problem. So our last graph that we've got here, they're asking us to compose a function with itself here. So in this case, we got to do the limit as x approaches -4 of f of x. So it's still the same. We just use the same graph for the whole thing, right? Because it's just f. So you're going to do the inside first. The first step, you're doing limit as x approaches -4 of f of x. And so if x is approaching -4, -4 is right here, what value do I get for that limit? We're going to this point right here. What's my y-coordinate there? -1. Okay, so the answer to that limit becomes what x is approaching on the second limit. So we're going to have limit as x approaches -1 of f of x again, because we're doing f of x. which side? Is it left or right or both? It's going to be left on this one because at that point, both of your lines are approaching from below. This is really important for this problem because does the limit as x approaches -1 of this function exist? It does not, right? It'd be so if it was both sides, you would get the limit does not exist. But the limits from the left and the right are different for this. This is going to be the limit as x approaches from the left. And so right here is our -1. So as we approach that from the left, we would go to this point right here. Y coordinate at that point is -5. So -5 would be our answer. So be careful with those. They can be really tricky. You got to, whenever you do that second part, you got to think about whether it's from the left or right or both sides. Okay. So our assignment, we've got two things we're going to do. Well, actually, are we going to do two things? Are we just going to do, let me look here. Okay, this assignment is what I used to give in the book, I think, but I have made a delta math. So I think I made the delta math. Let's make sure it's there. Let's do the delta. Have we used delta math in this class? We did. So you guys should already be in my delta math. Go to calculus. Okay. So let's just do the delta math and not the. No, that's not what I want. Calculus, and not the other. And this is going to have you do these primarily from graphs here. And I think it's got 10 questions. It shouldn't take you very long, I don't think. Some of them are confusing, some of them are not. Like if I look here, x approaches 8, that's that point I get 1. And then I got to do 1 from both sides, I'll get 2 for that one. So that'll be your assignment. We might go do a couple problems from that textbook stuff. Like I might just pull a couple of those from the warm-up because I think that part should probably be the easier thing. Also, tomorrow we are going to have a little small quiz. These are just little quizzes. They don't count big. They might kind of seem like they count big here at the very beginning because we don't have any grades, but it will be in homework section after that. I did make a practice quiz for it. This is optional. You do not have to do it. It is not extra credit. But if you're wanting to kind of see what the quiz is going to look like, it has got some of these. I don't think we did these on Delta Math, the numerical ones. It's asking you about like the limit as x approaches 3 from the left. So numbers smaller than 3 would be like 2.9, 2.99, 2.999. And so it looks like that's probably -1. You just type those in. Delta Math does the table there for you for those, just like we were doing on Desmos for that. So this will have a few different things to look at there. And we will have a short quiz tomorrow that's very similar to that one for that. So again, that's optional. The properties of limits is required. The practice quiz is optional. You can even do like part of it if you want. If you just want to flip through it and be like, oh, I know how to do that, know how to do that. Oh, I'm going to try this one because I don't know. I think I have it set where it should show you the answer after every question on that one. Let me check and see if I did that. But we got about 10 minutes here, so work on those things. I'm going to make sure I've got the... There should be some up here. It should show you, like, that practice quiz should show if you got it right or not after every question. So if you don't want to do every question, you'll be fine.